Should I start? Yeah. So hello, I'm Jose Luis, and I will present our paper about motion matching and body orientation prediction to animate VR avatars. So I will start with the motivation. So typically in VR, we have these upper body avatars that we can animate using the two handheld controllers by applying inverse kinematics using the controllers as an effectors. And then we use the head-mounted display to position this upper body avatar in the wall. But what happens if we want to have full body avatars like these ones? And so what we're doing in research is, okay, so just like we do with the arms, let's add more devices that can track our feet, for example. Let's add 2 devices and apply inverse kinematics. And then we can add another tracker. And so we can have on the pelvis or on the hips. So we can have more accurate positioning of the user. And then some other papers like et al., they only use one additional tracker and they use neural network to predict the lower body. So, but in standard VR systems, like we only have the 2 handheld controllers and the head on the display. So games, they need to apply traditional animation, fixed animations or track the character and so on. So what we want is only using the 2 controllers and the head-mounted display to be able to animate a character having natural looking animations in locomotion. Let's say, for example, here walking forward. So that's our paper. I will start with an overview. Our method consists of three main components. Let's see first an overview. First, we predict the body orientation of the user. This is an important step so that we can correctly, properly animate the character, because in VR, users tend to move a lot the head, and we really want to differentiate when the user is moving the head and when the user is actually moving the whole body. So we predict the body orientation with a neural network. We'll see later. Then we apply motion matching to have a first full body pose. And later we'll see in detail. And finally, we do a final pose adjustments, and we apply inverse kinematics to animate the upper body so we can have accurate hand positioning, which is very important in VR. So the overview of the system would be something like this. We have first the body orientation prediction. Then we have motion matching, which we base in the state-of-the-art implementation by Holden et al. In 2020 by Learn Motion Matching paper. And then we apply the final pose adjustment. So now let's see every component in detail. So first, the prediction of the body orientation. So for this, we use a simple feed-forward network, and we use the orientation, velocity, and angular velocity of the 3 devices, and the previously predicted body direction to have some continuity on the prediction. So we capture 2.4 hours of MoCap. We ask the user to play some MetaQuest games and HTC Vive games, as well as doing some of our VR experiments. So we have a VR-specific data set. And with this, we train the neural network. But actually, to train neural network, we don't do it like this, because the problem here is that this previous body direction is here with getting from the training set, so it's not predicted. So here, the neural network will actually only learn to copy the previous body direction into the predicted one, because we only in one frame the direction doesn't change that much. So instead, what we do is let's start as before, but now we concatenate the output of the neural network several times. For example, let's say 50 times. So now the neural network is this is during training, so it's forced to actually use the device's information to compute the body direction. So it cannot simply rely on the previously predicted body direction. And then the last one is the one we use to compare with our data set and do a propagation. So in real time, we will only use one neural network. This is just during training. So here you can see the differences, and in the center, the ground truth, and you can see like on the left, if we only train like normally, we get worse results, and if we train the neural networks concatenating them, we get better results. So that was for the prediction of the body orientation. So now for motion matching, I will make a summary. And so first we have our animation database, which is going to be an animation we capture with motion capture of a user doing some locomotion, like walking forward, backwards, sidestepping, turning, several degrees of turning, several velocities. So we have a database that represents all locomotion movements the user can do in VR. So from here we create the pose database, we extract the rotations, velocities, everything we need for motion matching to work, and the fit contact we will use later for foot lock. Once we have the pose database, we extract the main features for locomotion. So there is the velocity of the feet and the hip, and the position of the feet. So these two are the what is called the pose features, because they represent the current pose of the user, of the skeleton. And then we have the trajectory features, which represents where the character is moving towards the trajectory of the user. So this is going to be the future position of the character projected onto the ground, let's say 20, 40, and 60 frames ahead, and the same with the direction. So this feature database is what we're going to use for the search of motion matching. So, well, you can see here a representation with an idea of the features. In light blue, you have the pose features, and in dark blue, the trajectory features. So once we have our databases, motion matching will work in real time like this. We first get the track devices information. We predict the body of the direction, the body of the user. And then from the velocity of the head-mounted display, we compute the trajectory, we kind of predict the trajectory of the user. So we use the velocity and the body direction to create the trajectory features. And then we simply get from the skeleton the current pose feature, which is compute the position of the feet, the velocity, and so on. So this makes the query vector. So now motion matching is like a native network, so it's going to search in the feature database for the closest match to this query vector. So essentially what we are doing in the search is we are minimizing the current pose. So we are avoiding sudden changes in pose. And at the same time, we're trying to find a pose which consecutive poses will follow the trajectory of the user. Then what we also do is we get the height of the head-mounted display, and what we want to do here is we want the avatar to be able to squat or do different types of leg bending. So maybe with a video, okay. So we capture different databases. Oops. So we capture different databases with different levels of leg bending. And in runtime, we can, based on the height of the head-mounted display, we just change the database, and we have different, for example, the avatar can squat. So since we're keeping the pose features, like even if we change the database, the configuration of the feed will remain, and we also do blending between changes, that we have a smooth transition. So then the problem we have in VR is that we really want our avatar to be in our position. We don't want the avatar to go away from us when we are at first person view. So we have a problem, and it's first when we are predicting the trajectory of the user. It's hard in VR because the user can do anything, any type of movement. So it's hard to predict. And second, even if we knew the future trajectory of the user, the animation database of motion matching is limited. So we will have always some deviation. So what we do is to have some position accuracy, we limit our positional error. So let's say for us, for first person view, we don't want our character to move from the user more than 10 centimeters. So we just simply clamp this. And the problem is that if the avatar goes 10 centimeters away from us, we just simply drag it towards the user. And then that's when we introduce some foot sliding, you can see. So if we use a larger threshold, for example, for collaborative VR for our collaborators, and then we can have higher quality animations. So to minimize or fix the foot sliding, we use foot lock. So basically, we have the feet contact, and when the feet when we step on the ground, like we fix the leg, the feet, by applying inverse kinematics. And then we have the inverse kinematics for the upper arms. So what I was saying before at the beginning is in VR, we really want the user wants the avatar hand to be in the real position, in the position of the user hand, because users can notice any drift in the hand position. So by applying inverse kinematics, as most applications do for the upper body, we can get accurate hand positioning, and yeah, you can see here. So in our system, if one controller runs out of battery, or we want to use one hand-mounted display, we simply disable inverse kinematics for the upper body, and we have a full body animation by provided by motion matching. So here you can see some results of well, the avatar can walk forward, backwards. You can notice sometimes a little bit of drift. You can also let's see. So you can also turn in place, and you can have natural looking animations. You can look with the head, and the orientation of the body will be correctly predicted. And also we thought, okay, so there are a lot of dancing applications in VR. So let's try our system. So we change our locomotion database by a dancing database, and then we can have the avatar correctly animated while dancing, following the user. And if the user rotates, the avatar will follow while at the same time dancing. So this is just by changing the animation database, and the rest of the system remains the same. So to conclude, so we presented a data-driven approach to animate VR avatars, and we believe we can improve the animation of the avatars in VR applications, and it can be, our method can be used right away because we're only using one hand-mounted display and 2 controllers. We're not using any additional devices. And yeah, so that's it. Thank you very much for your attention. Do you have a project website? If you have any questions, thank you.
Any questions? We have some time.
Okay, so
can you repeat it, because I'm sure the people online haven't heard it. Can you say it a bit louder?
Yeah, can you hear me?
Yeah.
Okay, hear me. So I noticed, thank you for your wonderful job. And I noticed that you use IK algorithm in the former process. And I noticed you use handlebar and the headset as an end effector. And I wonder if is there any process to lock the foot slap, and can you describe how to solve the foot slats questions, and do you do any extra operation on the foot sliding?
okay, so how the foot lock works? So it's related to so we first compute the feet contact by we check when the velocity of the feet is 0, so then we know it's touching the ground. Okay, so then in real time when we get the animation, apart from the rotations and everything, we also get the foot contact. So then we have this boolean that when the feet transitions from being in the air to being in the ground, we store the position of the feet, and then we simply apply two joints 8K on the leg to fix we do it incrementally, so because we don't want to break the motion matching post. And yeah, it's we just, with inverse kinematics, we simply ensure that the feet is not moving until our foot contact level says again, okay, now the feet should go up, and then we release the. Yeah.
Okay, I see. Thank you.
Okay, just a second. Okay. Yeah. So,
nice work. I was really impressed with the fact that the height was changing. So it was the slot, but then also when they did the heel lift, you can actually animate in the avatar. And I was just curious to know if you evaluated the method on people of different height, to see how it reacted in those types of scenarios.
We haven't done much evaluation with users. We haven't had time. But well, what we do first is a simple calibration step. Like we ask the user to interpose, and then we store the height. But yeah, we haven't evaluated much on people.
Did you normalize the database for the height of the?
So yeah, it's not. Yeah, we could do that. We're not doing it currently. It's just we didn't focus on that. But yeah. Thank you.
okay, one last question, but I think the next paper should be getting ready to.
So you mentioned that it's important that the hands follow the motion of the actual human hands very closely. But now if you're walking around, because the motion for your feet is separated, so you're walking and you know from your body what your feet are doing, but what you see from down is a different animation. Isn't that pretty confusing? Like how does it feel to actually experience it?
Yeah, that's right. And for the lower body, it's just close to animation. It's not. I think it's not that confusing because people don't really look that much into the legs. They just want to look a little bit, see that everything's moving, and it's not that confusing. For the hands, it's super confusing. It really needs to be in the correct position. But for the legs, it's not that yeah. Well, we finished. Okay. Okay, thank you.
Okay, thank you, Jose Luis.